And I'm going to start recording this. Okay. So what I want to talk about here is non-ideal characteristics of transformers. Okay, so let's go back to our just basic, simple transformer, single-phase transformer. On a three-phase unit, this is applicable to all three phases, okay? If you take a look in Chapter 2, it's the first section of Chapter 2. Okay. A typical transformer, it's a coil wire, right? So it has, each coil has inductance and reactance. So what we do is we represent that reactance with a resistor and an inductor. And each coil has this, has resistance and inductive reactance. Okay. Now there's another component to this. It's called the excitation branch. That includes a parallel inductive reactance, J, X, and M, and RC. We call this IM. The current through that resistor we call IC. And this current right here, we call I/O. Okay. I/O is called the excitation current. For the transformer. So if it's excited from the primary, that excitation current is going to be coming in from the high voltage side, the primary side, okay? And concerning the magnetization branch or the excitation branch, I just want you to know what each one of those components are. We're not going to, I think the book might go through a couple calculations, okay? We're not going to do a lot. If we had a machines class, we would do these calculations, a few more of these. But when it comes to practical industrial electrical distribution systems, I think it's important to know the series components. What we're looking at right now are what we think of as the parallel components or the shunt components. And I'll tell you in a minute why we can ignore them. Okay, IM is known as the magnetization current. IC I don't want all my emails showing up in this video. IC then, C stands for the core loss. So it's a, RC is a resistance that represents the iron core loss. The core will heat up and vibrate, and there's a certain amount of power. It's not much, but there's a certain amount of power that goes into that core. And so we want to account for that somehow. Okay. XM is called the magnetization branch. Reactance. Okay.
The last one. What's the last one? Next one.
Reactance. Okay. But the bottom line here is RC and XM are very large. Compared to RP and XP. So we will ignore them. Another way to say that, another way to say the same thing is the excitation current I0 is a lot lower than I primary. Does that make sense? Okay. So we're going to ignore them. Makes our life quite a bit easier. There's lots of discussion. You know, we can play games with transformers all day long. We could move the excitation branch to the secondary if we want to. But we covered that the other day. When you move impedances through a transformer, how do they move through? We move them from one side to the other. They go up and down by do I remember this? Yep. The square of the turns ratio. Okay? So I'm going to put the turns ratio up here N. So we're going to ignore the magnetization branch, and I am going to just draw this transformer. First of all, we're going to start with I primary, JX primary, JX secondary, and R secondary. And it's an N to 1 turns ratio. Okay? Okay, now I just said it, impedances, sometimes they call it reflect. Impedances reflect through a transformer by the square by, I should just say N squared, by N squared. So the way this works out is Z secondary is equal to N squared Z primary. Is that right? I don't think that's right. It should be N squared Z secondary. Yeah, I have to multiply the secondary impedances by the square of the turns ratio to go to the primary. And then the converse is true. If I have an impedance on the primary, Z primary, and I want to represent it on the secondary, I divide by the turns ratio squared. There we go, that's correct. And that's what I want to do with X secondary and R secondary. And what happens is I can represent this transformer as I can represent the resistance of the transformer just on the primary side by writing this resistance as R primary plus N squared R secondary. And the reactance the same way. JX primary plus n squared x secondary. And it takes it from the secondary side. Yeah.
N squared times ds equals to CP, and CP equals to CS over n squared. Yeah, they're both equal to CP.
Oh, did I say that wrong?
Yeah. Looking at the book, yeah, I can input.
No. What I'm saying there, I think I have them written right. What I'm saying is if I have a secondary impedance and I want to reflect it to the primary, I want to make it a primary impedance, I have to multiply by the impedance squared, n squared. If I want to take it from the primary and go to the secondary, I guess maybe this should be Z secondary. Yeah. Thank you. Z secondary over Z primary. There we go. Yeah. That's better. Thank you. Okay? Yeah.
On your transformer, the turns ratio, is it
Yes.
n equals 1 or n to 1?
No, N21.
N to 1.
Yep.
Okay.
And we always, remember, N is always larger than 1 for us. It's always the high voltage divided by the low voltage.
Okay. That's even for, right now we're working with the non-ideal transformers.
Yes.
So even with non-ideal
Yes.
transformers, it
Yep.
would still be greater than
Yep.
1.
And if you look at this is an ideal transformer. So we're adding the non-ideal components to it.
Okay.
Okay? Okay? Now, we have a special name for each of these items. We call them the equivalent resistance. So, our equivalent, and usually they explain that this is reflected to the primary. Okay? So I might call it REQP is R primary plus n squared R secondary. X equivalent primary is equal to XEQ primary equal to X primary plus n squared X secondary. Okay? So then we can write Z equivalent equal to R equivalent plus J X equivalent. And we can call this the transformer impedance. Sometimes I call this the ohmic impedance. In the near future, we're going to get to the per unit system, and we're going to have to differentiate between per unit ohms and ohms. Ohmic ohms. Okay? Okay. Let's work example 2-1. Just to work with this a little bit. So we have a 50 kVA transformer, 1440 to 240, single phase, has the following equivalent circuit parameters. So let's just draw this. Our primary is 20.7. XL primary is J 40.5. And we have an ideal transformer. Okay. XM is 200K. And RC is 400K ohm. We have the secondary, and we have 0.08. R secondary, I should label these. R primary, and this is X primary. JX secondary equal to J 0.015. Okay. Okay. So the transformer supplying a rated load of point lagging power factor and 240 volts. Calculate the turns ratio, secondary current. So, I gotta see how they solved the problem to see where they assumed these voltages were at. So, oh, looks like it's running at rated load. So it's 50 kVA, and they're not real explanatory about this, but what they're saying is they've got a 50 kVA load out here, and the power factor is 0.9. Okay. Okay. The turns ratio, it's a rated 14.4 to 240. So what's that number turn out to be? 60?
Yeah.
So for A, N is 60 to 1. Okay. In B, they ask us for I secondary. Okay. And by the way they solve the problem, they're assuming that we've got 240 volts out here on the load. Okay. Now, the way I would do this is I would say I conjugate is equal to S over V conjugate, where S is equal to 50 kVA, 50,000, at what angle? Yes, 0.9 lag. So what are you doing? So it's lagging, so it's got to be so for the VA though, it's got to be positive. So it's positive, the inverse cosine of 0.9, right?
Yeah.
Okay. Over the voltage, 240 angle 0 degrees. So what do we get for I conjugate? Don't conjugate it yet.
To 208.3 at an angle of 25.84.
And so I then is 208.3 at an angle negative 25.84
Yeah,
amps, right?
yeah.
Very good. Okay, good. There's the secondary current. Okay, then C. In C, they ask us for the induced secondary voltage. What they're asking for here is this voltage right here. Let's call it Vs induced, SI. How would I get that? Now we're really going to rely upon your AC circuit analysis skills. I know the current, IS, so what would VSI be? Uh-huh.
Yes, so it will be, the secondary, plus, multiplied by the current in the heat, correct?
I think you're saying it correctly.
Yeah.
What I would say is it is VS, if I let this be VS, VSI is VS plus IS times Z of the transformer on the secondary. Good. So this will be 240, angle 0 degrees, plus 208.3, angle negative 25.84 degrees, times 0.08 plus J 0.015. Good number, Elijah?
I can give you what, IS times, the impedance on secondary is.
I went the whole number. Luke, you got it?
256.4 at an angle of negative 0.99.
Yeah.
What the book did? The book's got 242. What would we do different? Oh, this should be 0.008.
Yeah, 0.008. Yeah, I thought it was great that my numbers were, single close.
Sorry about that. Can you regurgitate that real quick and make a change? $242. Is it negative 0.5? Yeah. Volts. Good. Taylor?
What is the angle up there? Is that a 50 kVA?
Yeah. Right here?
Yes.
Yeah. We're calculating what theta is on the VA. It's the inverse cosine of the power factor.
Okay. That's right.
Get that?
Yeah.
See how I did that? I don't know if you guys have learned that trick yet, but in your Inspires, you can plug it in that way if you're comfortable. Okay? Okay? And it says it's a lagging power factor. That's where you got to remember that inductive bars are positive bars, so the angle on the VA has to be positive on the VA, so that we get a lagging current on the current. Get it? Okay, great. Now, Now, we really have to invoke, let's call it V primary, V pi I, V pi. Okay? Now, we know the turns ratio is 60-to-1, right? The induced voltage coming out of our non-ideal transformer is 242. So what has to be going in? 60 times that. It's a 60-to-1 ratio. And there's no phase shift across the transformer. So VPI has to be equal to 60. Let me write it as the turns ratio. N times VSI, or 60 times 242.9 angle plus half a degree. So VPI is equal to what?
That's like 14,574. Angle,
Good. Volts. What's E? Excitation current. Oh. How do we get that? Let me let everybody catch up here.
voltage primary, take the parallel resistance of.
Okay. So what I want to point out here is, now we've determined VPI. Well, VPI is the same as the voltage right there, which is the same as the voltage across the magnetizing branch and the core resistance. We know each one, so we can calculate the magnet. We can calculate, what did they ask us for? Oh, they asked us for I/O. They ask us for this, the excitation current. So we have to take the voltage divided by the parallel combination of the two. So I/O is going to be equal to VPI over, let me call it ZO, representing the complex impedance of the excitation branches, which is the VPI over RC in parallel with XM, which is equal to 14,574 angle 0.5 degrees all over. How do we do parallel with two branches? 1 over, what's RC? 400K ohm. Over 400K plus 1 over J, 200K, all that to the -1. Can you plug that in your percolator and get an answer? Get the correct answer? Want me to do it on mine here for you? That one you might need some help with. So what's our number? 14,000. Let me, there we go. 14,574 at an angle of 0.5. And I would do this divided by, and if I need extra parentheses, I'll just put them in. So it'd be 1 divided by 400 e to the third, end parenthesis. I'm going to put another parenthesis in there, plus 1 divided by, parenthesis, I, 200. exponent 3, end parenthesis, and I need all that stuff raised to the -1. I'll hit enter. And I don't have my parentheses right. So I'm going to copy it. You guys remember Control C and Control V works, right? So, let's see here. I think I'll just backspace through here and put in here plus 1 divided by parenthesis J 200 e to the third, and parenthesis. How about now?
You raise the -1.
Oh, I got the -1 in the wrong spot. Control C, Control V, backspace. What I want is parenthesis. Now, raised to the -1. How about now? There we go.
Yes.
Good. Okay. And I think what I'll do is do a Control J and bring that in. Zero point 08147 at an angle of -62.9, we'll call it 0.9 degrees, amps. Okay, good. Now, that's I/O. We also know, let's call it I primary. See what the book calls it. The book calls it I primary prime. So we know I secondary here, right? Well, we don't have to deal with I secondary being broken into the parallel excitation branch, okay? But we do know, if we know I secondary, we know I primary prime from the turns ratio. IP prime is going to be equal to I secondary divided by N. So what's that? 208.3. And what was the angle on that? -25.83 amps. So what do we get for I primary prime?
3.47.
What is it?
3.47.
3.47. Machine doesn't work. .47. 0.83 degrees, okay? And then what they're calling I primary is the sum of the excitation branch and I primary prime, I0. So we add those two together, 0.08147 at an angle of -62.9. Now, see what I was seeing earlier? Remember I told you there's a lot of times we can ignore the excitation branch? And this is why. Look at how low that is compared to the main current. It'll be here. Okay? It's a lot lower. I've worked in the transformer field, and guys that work for utility companies that are responsible for transformers, they're interested in the excitation current. Because if the transformer is not serving any load, to heat that transformer up, the power company still has to supply that. They usually look at what's called the no-load losses. because they have to pay for that, okay? It's the only people in the world that I know that are interested in that stuff. But it's good to know non-ideal transformer characteristics. When you're dealing with stuff, trying to troubleshoot stuff in the field, it's good to have a little bit of a fundamental knowledge about this stuff. So what's our primary current? Now, I primary then is going to be this current right here. What's that current? 3.53?
Angle of negative 26.6.
6.2. Okay. And F, G, and the applied H. So what's the applied primary voltage? So let's call this then V primary. So all we have to do is take VPI and add the voltage drop across the primary impedance, RP and XP. So V primary then is equal to I primary, V primary I plus I primary times Z primary. VPI was 14,574 at an angle of 0.5 degrees plus 3.53 at an angle of negative 26.62 degrees times, and I'm going to get it from the book, R primary was 20.7 ohms plus J, X primary, 40.5 ohms.
These are, those currents are amps, right?
Yes.
Okay.
$14,704.5. Angle of 0.866.
66 degrees, volts. Okay. Then the last thing they do is they ask you to, well, in I, they reflect everything to the low side, and then in J, they reflect everything to the high side. Yep. To be honest about it, I think what I would do is just reflect everything to the high side. So let's just do J. I guess that should have been I. R secondary to primary. So we multiply by n squared. So it would be 0.008 times 60 squared. And X secondary to the primary would be 0.015 times 60 squared. And the book gets 28.8 and J 54 ohms. Okay. And then what I was saying earlier, the other thing I might be inclined to write then is R equivalent and X equivalent. And then R equivalent then would be 20.7, well, so R primary plus N squared R secondary, or 20.7 plus 28.8. Now I think I get 49.5 when I do that. And X equivalent would be X primary plus N squared X secondary, and that would be 40.5 plus 54, and I get 94.5 ohms. And then I would additionally write then the equivalent impedance of this transformer would be 49.5 plus J, 94.5 ohms. And there we got one number that represents the total series impedance of that transformer. Okay? And I'm going to stop recording.